We define total internal reflection as that phenomenon that happens when a ray of light strikes a boundary at a big enough angle that it won't refract, but rather it will reflect. That happens in one situation and one situation only. You've got two indices of refraction, obviously. You've got to be going from the high index of refraction to the low index of refraction. In other words, the light has to speed up as it goes from one medium to the other. If the light doesn't speed up, you can't get total internal reflection taking place. You're always going to get some reflection, always. Some of the light will reflect, but most of it will refract in the case of going from low to high index of refraction, or even in a lot of cases when you're going from high to low. But total internal reflection will only take place when you're going from high to low, and when the angle is above an angle that we call the critical angle. Okay, if we draw a ray of light like this, okay, with a certain value of theta 1, okay, we know that that light is going to speed up. We know that that theta 2 is going to end up being bigger than theta 1. That's still not total internal reflection. You will, by the way, get a tiny little bit, whoops, not like that though. You may, or you will, get a tiny little bit of, still not like that, boy. More like this. A tiny bit of light reflecting. That's not what we're worried about right now, because again, the vast majority of this light will refract. If we increase the angle of incidence, though, then of course the angle of refraction is going to increase as well. The angle of refraction is almost 90 degrees right now. If we increase the angle of incidence a little bit more, like this, then the angle of refraction is 90 degrees. Total internal reflection has begun to occur. This angle, this red angle right here, theta 1, we're going to rename it theta c for the critical angle, the angle at which total internal reflection begins to occur. Here's what you got to remember when calculating the critical angle. Okay, when solving for the critical angle, which is really just a special value of theta 1, you're going to make sure that you make theta 2 equal to 90 degrees. The good news there is that sine 90, and that's what it becomes in your equation, sine 90, is always equal to 1. That means that term on the bottom of the equation disappears. We say sine theta 1, or sine theta c in this case, over sine 90, or over 1, just disappears, is equal to n2 over n1. Theta c becomes equal to the inverse sine of n2 over n1. And hey, told you yesterday, if you make a mistake with n1 and n2 and get them mixed up, go from low to high index of refraction, the good news is in these total internal reflection problems, your calculator is going to give you an error. So you should spot that. All right. One question, 3 parts for homework last night. We wanted to find the critical angle for each of the following. Any issues with any of those 3 questions? None? Well, let's try one of them, okay? Let's try one. Let's try diamond and air. The index of refraction of diamond is 2.42, and the index of refraction of air is 1.00. Which one's N1 and which one's N2? Doesn't say which way the light's going, does it? Just says, here's the interface. It's diamond, air. Doesn't say whether you're going from air to diamond or diamond to air. Which way are we going? John? Good. Got to be going from high to low index of refraction. Got to be going from diamond to air. Okay, that means that N1 is going to be diamond, from diamond to air. We're going to say sine theta 1 or sine theta c over sine 90, which is just 1, is equal to n2 over n1. We're going to say theta c is equal to the inverse sine of 1.00 over 2.42. So let's pull out our calculator and do this as a group here quickly. The inverse sine of 1 over 2.42. We do that, we get 24.4 degrees. Okay, which is exactly what we have here. Now, have a look at the other critical angles there. Water and air, 48.8 degrees. You still get light to reflect off of the boundary between water and air. We saw that in the demonstration that I did for you on the board here a couple of days ago with that podcast, right, where the golf ball was disappearing. The light was reflecting off of the water-air boundary. Okay, but it happens at a much higher angle than it does for diamond. Even for diamond and water, Okay, the critical angle is a lot lower than it is for water and air, but quite a bit higher than it is for diamond and air. The fact that the critical angle for diamond and air is so low allows you to get more reflection. It's easier to get bigger than the critical angle, easier to exceed it, which means you get more chance of causing total internal reflection inside that diamond. And that's why diamonds sparkle so much, right? Because you get more reflection taking place inside, partly because of the cut of the diamond at the right angle, but partly because the index of refraction is so high, the critical angle is so low, that it's just easier to exceed it. Is that good? All right, yesterday we do some ray diagrams. We do some ray diagrams for curved lenses. What kind of lens we got here? What is it? This is a converging lens, also called a convex lens. Be careful. Converging with lenses is convex. Converging with mirrors is concave. Rays that are parallel to the principal axis will converge at the focal point. This point right here on the other side that we call the focal point. This would be a real focal point. Let's draw a ray diagram for this particular situation where the object is in between F and, what do we call this, by the way? F and 2F. It's not going to be the center of curvature or the radius of the lens this time, right? Like it was for mirrors. Let's draw that first ray. Parallel to the principal axis, we know it goes down through the focal point. Second one goes, where does it go? Where does the second ray go? Somebody stop me. My hand's getting tired. John? Yeah, it goes down through the optical center. Now, there is a third one we could do, down through the focal point on this side, and then it would go, where do you think it would go? Parallel to the principal axis. But we never need to draw that one, because the second one always works here. We draw it through the optical center. We find that the two rays converge on this side. What would the characteristics of this image be? Yep. It's larger, it's inverted, and it's real. Good. Solid lines intersect. We could project it onto a screen, and we will in about 5 minutes project that onto a screen. Okay, let's try one more. For this type of mirror, that is, when our object, for this type of lens, when our object is inside the focal point. First ray, parallel down through the focal point. Second ray, where's this one going to go, Dallas? Optical center. It's going to go straight down. They don't intersect here, so what do we do? Tyler, what do we do if they don't intersect? Good. Draw dotted lines backwards, right here. Okay, at some point back there, they're going to intersect. Going to be about right there. What are the characteristics of this image? What's one of them, Sean? Larger. Good. What's another one? What is another one, Hayden? It's virtual because dotted lines intersect. It means we couldn't project it onto a screen. What's the third one? What's the third one? It's upright. It's upright, right side up. Got it? All right, I left you drawing some ray diagrams with concave lenses or with diverging lenses. I drew the first one. Those of you who actually completed this would have found that the characteristics of all 5 of them are exactly the same. Now, the image may change size and position ever so slightly, but the characteristics will still be the same. I'm going to draw 2 more just to demonstrate that, in fact, that's the case. Okay, let's draw the third possibility. First ray, okay, from top of the object parallel to the principal axis, it's going to diverge away from the focal point. Second one, down through the optical center. There they are. If we extend this backwards, and we've got them intersecting here now, right? But technically, it's not the solid line intersecting with the dotted. Technically, it's the dotted line going back, intersecting with the dotted. Okay, it's not critical, really, that you draw that second dotted line, because you can see they intersect. Just want you to know that technically it's 2 dotted lines intersecting, and that's important for us, because the 2 dotted lines intersecting tell us that it's what kind of image. 2 dotted lines intersecting tell us it's what kind of image. Virtual image, good. That it's a virtual image. We also know that it's upright. We also know that it's smaller. Okay, let's draw one more. This time way in here, inside the focal length. First ray, parallel, away from the the focal point. The second one is going to go down through the optical center. We extend these back. Again, we don't really need to extend the second one back, but technically we should. We find that the rays, the dotted lines intersect right there. Okay, that looks to be a bigger image than we had the last time, but it's still smaller than our object. It's still upright, and it's still, what's the third one called? Virtual, because dotted lines are intersecting. Got it? This is my favorite slide to put up this year. The reason that this is my favorite slide to put up this year is because it was the easiest one for me to prepare. Of the however many hundreds of slides that you guys see this year, this was the single easiest slide for me to prepare. The reason is, it's copy and paste. All I had to do is switch the word curved mirror math to curved lens math. I should have wrote everything down on it. That would have saved me from putting down the exact same thing on this page here today that I did on the other day when we did the curved mirror. The equations for curved mirrors, 1 over f is equal to 1 over do plus 1 over di. M is equal to hi over ho equals negative di over do. Those are the equations for curved lenses as well. The units, same deal. Centimeters, meters, miles, doesn't matter as long as you're consistent. Got to worry about signs though, positives and negatives. When is the focal length going to be a positive value? When it's a real focal point. When do you have a real focal point? When you have a converging lens. Now be careful though. You had a real focal point for mirrors when you had a converging mirror. But a real focal point for mirrors, a converging mirror, was a concave mirror. A real focal point for lenses, a converging lens is a convex lens. So concave and convex get switched around this time. It's still converging. Real focal point still goes with converging, but it's convex instead of concave. And of course, it's negative if you have a virtual focal point. DO, same deal. It's positive if you have a real object. The good news is for you guys, that's going to always be the case. Later on, maybe it's not, but Physics 30 it is. DI, the image distance, same deal. If you have a real image, it's going to be a positive DI. If you have a virtual image, it's going to be a negative DI. HO, HI. When's HO positive? If you have an upright object, same deal as it was with mirrors. Okay, and that's going to be the case almost all the time. And HI is going to be positive if you have an upright image. And of course, it's going to be negative if they're flipped over, if they're upside down, inverted. Finally, magnification. Again, same deal with magnification. The magnification is positive when the object and the image are both on the same side of the principal axis. In other words, they're both right side up. They're both upside down. It's the exact same deal. The only thing you got to be careful of here, is to not mix up convex with concave. If you use the terms converging and diverging, it's exactly the same. If you use the terms convex and concave, it's opposite. We have to be prepared for both. Convex, concave, converging, diverging. Okay, let's take a look at a problem here, guys. Page 681, 13.7, it says a 2.5 centimeter high object, that's going to be HO, is placed 10 centimeters, that's going to be DO from a diverging lens. Okay, we circle this, right? It's a diverging lens. That's going to make my focal length negative. I don't care whether it's a diverging lens or a diverging mirror. The focal length is negative. Now, be careful. If they had have said a concave lens, focal length would still be negative. But a concave mirror, it would have been a positive focal length. So again, diverging, that's the easier term to use. Converging, diverging, because we always know it's positive, negative. Doesn't matter whether it's lens or mirror. But if they use the term concave, convex, it can be negative for one of them. It can be positive for the other one. This is negative. It's a diverging lens. The focal length is 5 centimeters. I'm going to right away go down here and say f is equal to negative 5 centimeters. We want to determine the image distance, di, the image height, hi, and we want to determine the attributes or the characteristics using the lens equation, we're going to call it now. We won't worry about the ray diagram because we've drawn all the ray diagram possibilities, right, on that template that I gave you yesterday. Okay, let's go with the lens equation, or as we used to call it, the mirror equation. We're going to say 1 over negative 5. 1 over 10 is do, plus 1 over di. We're going to pull out the calculator. We're going to do our thing with that. We're going to say negative 5 x to the minus 1, subtract 10 x to the minus 1. And then we're going to flip that over. And we end up getting negative 3.33. I'm going to put the unrounded number down just in case I need that for my other equation here. But I'm going to round it here as well to 2 digits, negative 3.3 centimeters. Now the next equation, m is equal to hi over ho. Does this feel like the same thing? Yeah, it is the same thing, right? It really is the same thing as we were doing before. So this should go pretty quickly for us when we're doing our homework here. Hi, we're looking for. Ho is 2.5 centimeters. Di is negative 3.33. But let's make it negative 3.3333 over do, which is 10. Oh, what's that going to be? I don't know, 0.83 or something like that? 0.83? I'm going to say 0.83. If nobody tells me different, then I'm going to assume that's right. What'd you get? 5 over 6? I think that's 0.833, isn't it? Give me a decimal number, somebody. 0.83? Yeah. And it's going to be positive because it's negative, right? Okay, attributes. What do we know about this? Is it larger, smaller, same size? Smaller, right? The object was 2.5 centimeters tall. The image is, no, it's not. Is that 0.83? Yeah, no, that's right. I think that's right. The image is only 0.83, so it's going to be smaller, clearly. What else do we know? Is it going to be right side up or upside down? Well, the image height is positive, so that tells me it's going to be upright. And finally, what else we got here? Real or virtual? Somebody tell me, real or virtual? Virtual, how do you know that? Okay, yeah. Yeah, that's exactly what Janessa said for the quiz, right? If it's a diverging lens or mirror, it's going to be a virtual image. If it's converging, then all bets are off, right? Okay, but that logic works perfectly fine if it's a diverging mirror or lens. The other way to determine it is di is negative, which means it's got to be virtual. And that works in more situations, right? All right, good. Here's your homework for tonight. Page 681, number 1 to 3. See what you can do with those, please. That's it for today.